Good morning. Welcome to this next OpenCloudification webinar, brought to you today by the OpenCloudification team. So my name is Ulrich Salzachs. I'm the Managing Director of the association called LSEG. We are together with a couple of partners in facilitating new developments on activities such as cloud technologies. And specifically over the last year and a half, more or less now, we have been working on trying to get developing cloud technologies better to an audience of innovative companies, both here in Flanders as well as in the rest of the world. So it's really about helping out in understanding some open cloud technologies, what that means, and how to implement those. What they also can mean in respect of comparison to public technologies in terms of private cloud technologies. But on the other hand, we also support these companies in making that transition if needed. So focus is really about everything in relation to technologies which are openly available, open sourced in the cloud. We had a very nice session last time about open technologies. And we also look very much into platforms such as cloud native in trying to specify and select a number of technologies which are developing there and making sure that they can be picked up by companies in a wider environment. So one of these things has to do with microservices, but also capabilities of edge computing. Or if you want specific components like key management in the clouds, like backups and so forth. Today we'll be talking a little bit more about infrastructure as code and ensuring uptime. But before we do that, a bit more about OpenCloudification. So what we aim to do with the activity, and it's a project that runs for 3 years. We do that together, as you can see, with Beacon, with IMEC ID Lab, and then ourselves as LSEG. And today will be hosted by the partners from IMEC ID Lab. And so what we aim to do here with all of these open cloudification activities is really to bring some of the expertise available from a theoretical perspective, some of the technologies that have been studied, and helping you putting them into practice by providing these types of webinars, also by working on and providing some white papers and a sandboxing environment that can be used for this matter. So if you would like to take this a step further, then we as LSEG and also some other of the partners have some specific tools to help you out in doing so. Our latest tool is called KISME. It's basically a program that is there to support cybersecurity with micro enterprises and small and medium-sized enterprises, really to support the transition towards better security. And that is definitely also the case for companies who are working with cloud technologies, with open cloud technologies, and are trying to understand the better perspective of their potential vulnerabilities. And we will be able to help you out also in understanding which technologies you can use to do better secure basically your cloud-based environment. So that is what we will be doing within KISME. We have a number of partners to do that, and so we'll be selecting on the case-by-case basis on how to specifically improve the offering. And that is something that you can expect also from us in the next couple of months to further clarify about. But having said this, please do give us a call or contact us directly and make sure that we can follow up together with you. The last program, the KISME program, is really on a European basis, so not only Flanders based, but happy to support therefore also non-Flemish and non-Belgian companies in that respect. So for now, please welcome also together with me Marlijn Sebrechts from ID Lab, IMEC. Good morning, Marlijn. How are you today?
Good morning. I'm very well.
Are you ready for the next Marlijn Sebrechts presentation on OpenCloudification?
Yeah, I just need a permission for screen sharing.
Yes, that's active right now. So the usual security settings applied here too. But you should be able to do that right now. There we go.
All right.
I'll hand it over to you, and thanks again, of course, for doing this, and looking forward to speaking to you later.
Great. Hello, everyone. So you can see the first slide, and now you should be able to see my introduction.
Right.
So I am Marlijn. I'm a senior researcher at IMEC, working on managing services in cloud and edge environments. And I also teach at the Ghent University, and I'm also part of the Ubuntu community. I'm currently seated in the Ubuntu Community Council and did a lot of work in the Ubuntu project. So today I'm going to talk about infrastructure as code. Infrastructure as code is an important step to level up how you are benefiting from the powers of the cloud. It's an important requirement to really use the robustness capabilities of cloud computing. I'm first going to talk about what is infrastructure as code specifically and why would a company want to use the infrastructure as code methodology. Then I'm going to talk a little bit about the different concepts inside of infrastructure as code. I'm going to give a quick overview of the landscape of infrastructure as code tools, because as any environment, there's a lot of different tools in there for different use cases. Then I'm going to talk about basically what is the current and the future of infrastructure as code, the cutting edge of infrastructure as code, and that's the paradigm of Kubernetes as an API. Finally, I'm going to talk a little bit about design patterns in order to implement infrastructure as code best in your company. And then I'm going to end with a little bit of a peek into the future of declarative Linux. In about an hour, we will have a short break. So infrastructure as code, what is it specifically? Infrastructure as code is in the context of operations. So what we traditionally call IT system administration. This talks about the initial deployment of servers, provisioning servers, configuring operating systems, installing services, and deploying the software that your company builds. This is also about maintenance, upgrading servers, upgrading operating systems, upgrading services, and upgrading software using CI/CD systems. And so the idea of infrastructure as code is basically to automate every part of operations, every part of system administration using infrastructure as code tools. So it's basically the idea of applying the tools we already have for developing software and apply those to infrastructure and platforms. The practices and tools that we have for software engineering, things like CI/CD, version, code versioning, and things like that, to apply them also to system administration. And infrastructure as code is a very broad concept that goes from managing everything from the actual infrastructure, cloud resources, virtual machines, storage, database as a service solutions, to actually managing the code that you deploy. However, as you see in the title of this slide has a sort of triangle. This is to denote that infrastructure as code is mostly focused on the left side of this slide, cloud resources, operating systems, and applications, and is less focused on CI/CD. Often when people talk about infrastructure as code, they're more talking about the left side of the slide than the right side of the slide. Nevertheless, CI/CD is an important part of your cloud journey. So before we had automation, let's take a short look at the manual approach of system administration and what were some of the issues with doing manual system administration, specifically in the cloud. So one of the issues with the manual approach is configuration drift. Configuration drift, it's the concept that when you have a bunch of virtual machines in the cloud that basically have identical roles. For example, you have a web application with a database that is scaled out, or with a web server that is scaled out. The initial goal is that every single one of the virtual machines that has one instance of the scaled web server, it should be identical because they perform the exact same functions and they're behind a load balancer. So all requests, it shouldn't really matter which virtual machine they go to because they are identical. However, what we see is that with manual configuration management, over time, these virtual machines do not become identical anymore. Let's give you an example. So for example, imagine that it's Friday afternoon, it's 4 o'clock, and suddenly you get an alert from one of your systems. It runs out of memory, for example. So you SSH into this server and you see, oh, there's actually an issue with the Java runtime here. There's a memory leak in the Java runtime, but I see that it's already fixed in the latest version of the runtime. So let me just quickly upgrade to the latest version. And then it's 5 o'clock in the afternoon and you're like, great, now I can go home. But by the time you're back at work on Monday, you might have already forgotten that you upgraded the Java version of this one server, and that you should actually also upgrade the Java version of all these other servers, since if there was a memory leak in one of the servers, it probably is also the case in the other servers. And so these kind of configuration drifts, they accumulate over time, and they end up to a point where your different systems are so different from each other that you start to lose trust in your infrastructure. So for example, let's say you are doing a big upgrade of the software version of your application. You're doing a big upgrade to a new version, which might break things. But you have a well-defined process. You try it out on one of the instances first, and then test if everything works. And then only then do you apply the upgrades to all the other servers. However, if you have configuration drift, then you have a big issue here, because it might be that this upgrade, that it works on one of your servers, but that it doesn't work on the other servers because they are using different versions of libraries or different versions of the Java runtime. And so as a result, your infrastructure is not robust anymore. You start to lose trust in your infrastructure. And you start to have a lot more failures. Another issue with the manual approach is scaling. If we look at large cloud companies like Facebook, like Amazon, like Google, the scale of their applications is almost incomprehensible. A survey a few years ago showed that Facebook has a single system administrator for every 20,000 servers. So this obviously means that if this single system administrator, needs to manually reboot 20,000 servers, that's simply not possible. And so that's another driving factor for automation, is in order to be able to scale the work of a single system administrator to very large number of servers, 20,000 servers in the case of Facebook, for example. And then another issue is, what if stuff goes wrong? For example, in a hypothetical scenario, you're using a major European cloud provider like OVH Cloud, and in a hypothetical scenario that definitely didn't really happen, one of their data centers is burning. Then you're like, okay, but there's no problem. We are quite far in our cloud journey. We have our infrastructure load balanced and duplicated to different availability zones inside of the data center of OVH Cloud. And so if part of the data center goes up in flames, then the other availability zone will keep working. And so that means that our infrastructure will keep working. However, if you look at this picture of this fictional event, you see that this is the first availability zone of OVH Cloud. This is the second availability zone of OVH Cloud. As you can see, both are actually on fire because they're way too close to each other. And as a result, when one availability zone went down in OVH Cloud, the other availability zone also went down. And as a result, a lot of companies lost their entire infrastructure. If this happens and you're doing everything still manually, then you have a big issue. However, if this happens and you're using infrastructure as code, then you just have a few hours of frustration, and afterwards your entire infrastructure is back online again. Let's look a little bit at the difference between fault tolerance and disaster recovery. What you see here on this picture, this is a worst case scenario. This is what we call recovering from a scenario like this is called disaster recovery. So fault tolerance is basically what if a single virtual machine goes down. This is something that happens quite often, and this shouldn't require a manual intervention to keep the services working because it happens so often. And this basically just means you have more instances of something and you have health checks and a load balancer. And if the load balancer sees that one of the backend services is down, then it simply just points the traffic to another of the backend instances. And there is often manual work needed, but the manual work is not needed to keep your service online. The manual work is needed to get duplication back. So if you have two database instances, one goes down, then you need manual work in order to recover that one instance that went down. But meanwhile, your service still keeps on working. However, if the entire data center goes up in flames, then you're in the field of disaster recovery. The only way how you can easily handle such a failure is to have everything as code, to use infrastructure as code, and then use that infrastructure as code in order to get everything back up as soon as possible. So obviously, in order to solve these issues, a lot of companies started looking at automating system administration. And the first step in doing that is these companies start to write a lot of scripts in order to install servers and automate their operations. But there is a big issue with scripting, and that is what we call the automation fear cycle. The automation fear cycle, it stems from the fact that initially you use the scripts in order to install the initial version of your software on your servers. You have a script that cleanly installs everything that your application needs. It installs it on a clean virtual machine, and then you have your infrastructure and it works. However, what happens when one of these servers, when they crash? What happens again? It's Friday afternoon and one of the servers is out of memory, and you try to see what the problem is. You upgrade the Java version, you see that that fixes the issue. Now you have configuration drift again. And this is the first step in this automation fear cycle. You make changes outside of your automation tool. You have configuration drift, which means that your servers are inconsistent. And the problem with scripting is that scripting, it basically explains every single action, every single command that needs to be executed in your on your server. Which means that if servers are inconsistent, if you have configuration drift, and for example, your script adds a certain line to a certain configuration file, But in some of the servers, this line was already added, and in some of the servers, this line has not been added yet. And then you run your script, then you could break certain stuff. And so because the servers are inconsistent, system administrators using scripting, they are often afraid that running their script will break something because not all servers are using the same versions, the same configuration files. Not all servers are identical. So when a small thing needs to be fixed, instead of changing their automation script and then rerunning their automation script, they actually make changes outside of their automation tool, even more changes, even more configuration drift, even more inconsistency, and they're even more afraid that their automation tool will break something. And so as a result, what we often see with companies that heavily invest in using scripting to automate their IT operations is that they only use the scripts for the initial deployment of servers. They stop using the scripts for the actual second day operations, for the actual maintenance of their servers. And this is an issue because most of the time, most of the energy is spent on maintaining systems, not creating clean new systems. So in order to solve the issues with automation, the second step is to actually use infrastructure as code. And this means what it describes. So infrastructure as code, it means you have code that describes your infrastructure. So let's use an example. So let's say that you know the end result of your servers. You know this version of Java needs to be installed. These configuration files need to have these values. This needs to be that. The idea of infrastructure as code is that you create a desired state model. This is a model that describes the desired end result of your servers. What version of Java do you need? Which services need to be started? Which software needs to be installed? It's basically if you have a maze, you basically just say, this is where I want to get to. And then the automation tool, it looks at the current state of the system and then creates a bunch of actions in order to get to that desired end state. And this has the advantage that if you have a number of servers and each server has a slightly different initial state, you will still, with using desired state models, using infrastructure as code, with the same desired state model, you will get all the servers in the same resulting state, even if their initial state was different. And so the automation fear cycle, because you made manual changes to your system, the automation fear cycle doesn't really happen because your automation tool can spot these differences and take different actions on each server depending on what the current state of that server is. So let's take a look at the difference between scripting and infrastructure as code. So scripting is basically you using a script that changes infrastructure directly, a script that has a bunch of commands that change the infrastructure, that execute certain scripts, that install packages, that change configuration files. While with infrastructure as code, what you as a system administrator create is simply a description of what is the end state that the server needs to be in. And then the management software itself, it looks at the desired state, it looks at the current state, and then takes the necessary actions to get from the current state to the desired state. That's the difference between scripting and infrastructure as code. So let's take a short look at the history of infrastructure as code. It all started with CF Engine. In 1993, Mark Burgess was a theoretical physicist who was maintaining the IT systems of the physics department. If you go look at the history of a lot of modern day software concepts, a surprising number of modern day IT concepts have been created by theoretical physicists who were managing the computers of the physics department, and then noticed that they actually liked computers more than the physics that these computers were computing. So Mark Burgess, he created the idea of convergence. This is the idea of user describes the final state, and then the software decides what actions are needed to go to that state. This is the idea of a declarative description of the desired state with an unpredictable, which allows you to go from an unpredictable initial state to a predictable end state. He compared this to a black hole. So a black hole basically gets every single element around that black hole from an unpredictable initial state. Like it might be a planet, it might be a sun that it's next to the black hole. It might be in different locations, unpredictable initial state, but eventually everything will be sucked up by this black hole and will be pure energy in the middle of the black hole, which is a predictable end state. I'm not sure if this explains the concept better, but given he was a theoretical physicist, he really liked this explanation. So let's take a quick look at what I just explained of imperative versus declarative. Imperative means that you describe not the end result that you want, but you describe the steps in order to get to that end result. A for loop is a great example of imperative programming. You are saying, okay, step over this array and change each element of this array. First change the first element, then change the second element, then change the third element. Imperative programming is often a very natural way in order to program steps, but this has the issue that the computer needs to take the exact steps that you have described in order to get to that end state, even if there would be a better way to get to that end state. And so declarative programming, MapReduce, is a great example of declarative programming. Using the MapReduce pattern, you don't describe how to get to a certain end state, you describe what the end state should be, and this allows the compiler and the runtime to figure out the most efficient, the most optimal path to get to that end state. That is why a lot of distributed data frameworks and a lot of performance systems that are very performant, that's why these systems all use declarative programming techniques so that they can find a more optimal way to get to that end state. So the desired state principle is a declarative configuration management design pattern. The user describes a model what the desired state is, and the system takes the actions in order to get the server into that state. Kubernetes is a great example of a piece of system administration tool that uses the desired state principle. You go from an unpredictable initial state to a predictable end state, and that basically means that you solve the issue of configuration drift. So this again, the configuration management system, it decides what steps are needed to get the system into that end state. Then I want to talk a little bit about idempotence and convergence, because these are words that you often see when you are looking into the documentation of configuration management systems. It basically describes how the system achieves the desired end state. Idempotence means that running an action twice gives you the exact same result. So that basically means that every single time your configuration management system wants to get a system into a certain desired state, it simply runs all actions, knowing that if the system is already in that state, those actions will give you the exact same result. However, convergence means that the config management system, it actually checks if an action is needed and only runs the actions that are needed. This means that if your system is already in the desired end state, then a convergent system will not do anything, which means that no ops, no operations runs where nothing actually needs to change are a lot faster in systems using convergence. So a simple example, idempotence means running the command mkdir-p, for example. If this directory already exists, mkdir-p will simply not do anything. While with convergence, it means basically executing, checking if the directory already exists, and only if it doesn't exist, then you create the directory. Interestingly, for no operations, the script on the right actually goes a lot quicker than the script on the left. Even though mkdir, even though that command itself, it also needs to check whether or not that directory already exists, the one on the right will still go quicker. And this is because in order to execute the mkdir command, your script needs to create a new process in order to run that command in. This creating of a new process, this is, in most cases, this is the main overhead of running this command. On the right, checking if that directory already exists happens in the same process. This is done by your script itself. And because of that, there's a lot of overhead that you don't have with the convergent approach. I want to add to this that Linux is inherently not declarative. Every tool, every declarative system administration tool basically wraps imperative Linux commands in declarative interfaces. However, this is something that is slowly changing. There are a lot of efforts underway to make Linux user space completely declarative. I will talk a little bit about that at the end of this presentation. So the goals of infrastructure as code, to summarize, the goals of infrastructure as code are to improve consistency and reliability by reducing human error, reducing environment drift or configuration drift, and creating self-documenting infrastructure. Because if any person wants to know, for example, what version of Java are we using on our servers, they can just look at the infrastructure as code, see what version of Java is written there, and that is definitely the version that's running in production. It also allows you to scale the work of system administrators and speed up deployment, change, and recovery by increasing reusability and automating IT operations workflows. Okay, so that was a short introduction into the concepts and history of infrastructure as code. But let's go a little bit more practical and look at the landscape of different tools. These are some of the most important infrastructure as code tools. Although I want to add, I am not talking about SaltStack anymore, for the simple reason that SaltStack very recently, so SaltStack is an infrastructure as code tool that is part of VMware. And as you probably know, VMware was recently bought by, I think it's Broadcom. And as you probably heard, Broadcom took an axe and went into the VMware product offering and started canceling a lot of products and started firing a lot of people. And some of the core maintainer of SaltStack has actually been fired from VMware. And so it is very unlikely, in my opinion, that SaltStack will remain will remain a competitive offering in the future. from my perspective, it seems as if SaltStack is on life support at the moment. But this isn't much of an issue for companies starting out with infrastructure as code, because there are many other tools that provide very similar offering. So the first tool I want to talk about is Ansible. Ansible is one of the most widely used infrastructure as code tools created by Red Hat, part of IBM. Ansible is an imperative configuration management tool, but it is also, it's actually sort of hybrid. It's both imperative and declarative. It's agentless in the sense that you run an Ansible command on your own laptop. That Ansible program will then SSH into a server to copy code to the remote machine, then run that code on the remote machine, and then exit. And once Ansible stops running on your laptop, it also stops running on the server. There is no agent that keeps running on the server. You're basically using Ansible. You modify servers by executing modules. Each module is a Python script that runs on servers and changes the configuration of that server, and modules take certain input. And this is where Ansible becomes declarative, because many modules use a desired state principle. For example, some modules, you basically say this configuration file needs to look like this. And then the module itself will take a look at the configuration file and then change the lines that need to be changed. Ansible is completely cross-platform, although Ubuntu is the most popular platform in the Ansible ecosystem, even though it has been created by Red Hat. Ansible is great at managing operating systems, and it's great at managing applications. You can also use it to manage cloud resources, cloud infrastructure, to provision virtual machines. However, I would not recommend it for those purposes, because there are better tools to use that actually to use for that purpose. Ansible, the desired state models in Ansible are called playbooks. There's two ways in order to use Ansible to change the state of a server. Either you run a module manually and you supply its configuration in the command line, or you describe your desired state in a playbook and then you run that playbook. And so here you see, for example, in order to install Postgres, you simply state, this is the package that I want installed, and this is the state I want this package to be in. And so this is clearly declarative, this is clearly desired state. However, what is important to note here is that these tasks, they are imperative. So each task will be run one after the other. So for example, if in your first task, you install a certain piece of software, and then you have another task that starts that piece of software, then you need to ensure that the task installing the software is above the task starting the software, because it will execute these tasks one after the other. And so this is infrastructure as code. This gets my approval as infrastructure as code because the inputs to these tasks are actually desired state. So a task is a single execution of a module. A play is a file with a collection of tasks subdivided in plays, and they are statically reusable. And with statically reusable, I mean that if you want the exact same infrastructure, you can just take a playbook and run it. However, if you want to change even a tiny part of that infrastructure, you need to go into the playbook and change values inside of the playbook. However, if you want a templated playbook, that's called a role. A role is a templated collection of tasks and related content, and this is dynamically reusable. So if you go into the Ansible repository, the Ansible online repository, you will see a lot of Ansible roles, for example, in order to install a Kubernetes server or install a database. And these will allow you to change certain configuration values without actually having to modify the infrastructure as code. There is a very large ecosystem. So you have Ansible Engine, that's the client CLI tool. You have Ansible Galaxy, that's an online repositories of modules and roles. However, do note that this online repository, this is a lot of these playbooks are created by volunteers. So you're not actually sure what the quality is of these playbooks. And then you have Ansible Tower. And Ansible Tower is basically an enterprise offering that gives you a control server so that you don't need to run the Ansible scripts from your laptop. You can actually just submit your desired state models to the Ansible Tower, and then the Ansible Tower, it will run Ansible and connect to the different servers in order to get those servers into the desired state. Second tool that I want to talk about is Terraform. Terraform is a tool created by HashiCorp, and it is 100% declarative. You can create desired state models either using the Terraform domain-specific language HCL or by using JSON. I would recommend to always use HCL simply because there are a lot more resources available online in terms of documentation and things like that, in order to figure out how to actually use it. You will often have a much easier time if you simply learn a little bit of HCL, because it will be much easier to get support online. HCL is also a very, very easy language to learn. You basically change virtual infrastructure. It's also an agentless tool. You run it on your laptop and it then connects to the cloud in order to deploy that infrastructure. And it's cross-platform and cross-cloud. However, I want to make a small note to the cross-cloud part of Terraform. Terraform modules, your desired state models for Terraform, they are not cross-cloud. If you create a desired state model, for example, that explains, okay, in Amazon, AWS, I want these virtual machines, I want this database, I want this network, that's the virtual infrastructure that I need. That desired state model will only work on Amazon. It will not work on Google Compute Engine. It will not work on Azure. Once you've written your desired state model, it will only work on that specific cloud provider. This is because your desired state model will use a lot of the cloud provider specific concepts. This is an advantage in the sense that it's an incredibly flexible tool, and you can use every single resource in AWS, for example, is available from Terraform because it doesn't abstract anything away. You have the full power of AWS using Terraform. But it has the downside that if you ever want to move your virtual infrastructure to another cloud, then you basically need to rewrite your desired state models. You can still use Terraform, but you need to rewrite your desired state models. So Terraform is great at managing cloud resources, cloud infrastructure, database as a service, or virtual machines, or virtual networks. You can also use it to install operating systems and install applications on those operating systems. But again, I would not recommend that because tools like Ansible are much better for that. So as a result, what we often see is a combination of using Ansible and Terraform together. Ansible is used in order to manage the operating system, manage the application on top of the operating system, and then Terraform is used in order to manage the virtual infrastructure and basically kickstart Ansible. Okay, so let's take a short look at the different concepts of Terraform. So Terraform configurations are code written for Terraform. Terraform configurations, that basically how they call the desired state models. They call them configurations. Terraform providers are plugins for Terraform that you use in order to manage cloud resources. For example, there is a Terraform provider for AWS, for Google Compute Engine, for Azure, but also for Kubernetes and for VMware. These providers allow you to use Terraform to deploy resources on Kubernetes, on AWS, on VMware vSphere. Then Terraform modules are reusable Terraform configurations. So providers are the plugins that let you connect to certain cloud providers. Modules are reusable desired state models. And then the Terraform registry is the online repository where you find everything. You find modules there, you find providers there, and you can use it. It's a very good resource for high quality modules and high quality providers. Terraform configuration, you can see on the right, this is an example of a Terraform configuration that basically ensures that there is a single virtual machine running inside of AWS. You use Terraform by writing a configuration, then you run Terraform init, which will download the required providers. You run Terraform plan, which will look at the current state of the cloud infrastructure, look at the desired state, and then generate basically a diff, a change log. This is everything that I'm going to change in order to get from the current state into the desired state. Then you run Terraform apply in order to actually apply this configuration. Then you run Terraform show in order to look at the current configuration, the current state in the cloud. And then you run Terraform destroy in order to remove everything. However, very important, you can, in your desired state, you can lock specific resources. Locking specific resources is a good way to ensure that those resources will never be removed, even if somebody makes a big mistake in their desired state, which tries to remove your entire infrastructure. For example, if you are using backups, if you are using databases, it's a very good best practice in order to lock all those resources in order to ensure that if you ever accidentally destroy certain infrastructure, that those backups will never be destroyed. There's this famous issue that happened a few years ago where a large cloud company was using Terraform and they had an intern come into their company. And the intern wanted to learn Terraform. And so what the intern did was they took the infrastructure as code description of the company's infrastructure. They removed everything, changed it into a single virtual machine in order to test it out, and then run Terraform apply, not looking at the changes and then just executing everything. And the entire infrastructure of the company was removed. This is why it's very, very important to always look first using Terraform plan, to always look at, okay, what are the changes that Terraform is actually going to do? Because if you have a whole bunch of stuff running and then you tell Terraform, now my desired state is only a single virtual machine, then Terraform will remove everything that is already running. So be very cautious with Terraform. It's a great way to destroy an entire cloud company. Terraform modules, as I've explained, are reusable configurations. For example, how to install a Kubernetes server, how to install load balancers or databases. And basically, there's a workflow that I already explained. So you write your configuration, you run Terraform plan and Terraform apply. But I also want to explain that there is an easy migration path. If you already have cloud infrastructure and you want to start using Terraform to use that cloud infrastructure, you can actually do that by using the import functionality, the Terraform import functionality. This allows you to import already existing cloud infrastructure into Terraform and then create a desired state configuration from that. Now I have to give a disclaimer about the elephant in the room. Terraform as a tool is not open source. Terraform uses the business source license. The business source license is basically a source available license, so you can look at the Terraform code base, but there's a whole lot of restrictions of how you can actually use Terraform tool and the code of Terraform. Specifically, you are not allowed to use the product if you compete with HashiCorp. And for those of you who know HashiCorp, HashiCorp has a lot of different offerings. So a lot of companies that are providing platform as a service offerings or software as a service offerings, they cannot actually use Terraform itself. The business source license does have a certain backstop. If HashiCorp, the company, ever goes out of business, all code that is a part of Terraform becomes open source after 2 years after it's been created. However, if you want to keep using Terraform, even though you have a business that's competing with certain products of HashiCorp, you can actually just use OpenTofu. OpenTofu is an open source fork of old Terraform code. Terraform used to be open source, and so the OpenTofu is an open source fork of old Terraform code, which is completely compatible with Terraform 1.5. It is a Linux Foundation project, so it is supported by quite a large community. However, if you look at the rate of development of OpenTofu versus Terraform, the rate of development for OpenTofu is slower than Terraform itself. But with Terraform, you only have a single company working on it, while with OpenTofu is supported by a much larger community of different companies who all have invested in continuing the project. This already explained. Then another tool I want to talk about is Chef. And Chef is a very frustrating tool if you want to use Google while you're doing system administration work, because Chef uses very confusing terminology. For example, desired state models in Chef are called Chef cookbooks. And so if you Google for Chef cookbooks, then you will not find anything about this configuration management tool, Chef. Then you will just find resources on actual cookbooks and how to prepare meals. Chef Chef is a tool that's written in Ruby, and you write your desired state models in Ruby. And so this means that Chef itself is actually an imperative tool. You basically write your configuration models, your desired state models using the Ruby programming language. However, very, very similar to Ansible, Chef is a hybrid between imperative and declarative, because in this desired state model, there are a lot of resources. And these resources, they use the desired state principle, they are declarative. So because of that, Chef is also hybrid between imperative and declarative. Chef has an agent, the Chef infrastructure client, which connects to the Chef infrastructure servers to retrieve models. Chef is also cross-platform, but very similar to Ansible and Terraform. Your desired state models are often not cross-platform. Even though you can use the same tool on different platforms, the desired state models that you write are often locked into a single platform. Chef is a product that is much more focused to enterprise, and so it has a very, very large ecosystem. Chef has a very large ecosystem of enterprise products to integrate with enterprise workflows and authentication mechanisms and single sign-on servers and things like that. Chef is mainly focused on managing operating systems and applications, although you can also use it for CI/CD and you can also use it for cloud resources. I would not necessarily recommend using Chef to manage cloud resources and to manage code, to manage CI/CD pipelines, simply because there are much better tools to actually do that. So this is an example of such a resource. Package MySQL server. I want that server installed. On the right, I just wanted to add this little example here. This shows that it is actually technically possible to write cross-platform desired state models using Chef. However, then basically every single thing you write will be a case statement. Okay, if we're on these operating systems, do that. If you're on that operating system, do that. If you're on a different operating system, do something different. So in my opinion, this is not cross-platform. Chef is cross-platform in the sense that you can use the tool on many different platforms, but the code that you write will not be cross-platform. Chef cookbooks are templated models of desired state. A cookbook contains multiple recipes, a recipe contains multiple resources, and the resource describes the desired state of a certain component of your server. Community code is shared in the Chef Supermarket. Chef Supermarket is another amazing name that is incredibly search engine optimized, so that every single person typing your name into Google will end up in the tool instead of in websites for actual supermarkets. Yeah, it's very difficult to Google things when you're writing, when you're using Chef for system administration. Then I also want to talk a little bit about Puppet. Puppet is an alternative to Chef and Ansible. It's a 100% declarative alternative. You use the Puppet programming language in order to describe the desired state of your infrastructure. However, very similar to Terraform, declarative means that the order of execution is not guaranteed. It's not because, for example, you first write this piece of software needs to be installed, and underneath that you write this piece of software needs to be running. It's not because you write it in that order that it will be executed in that order. That's why when you use Puppet or when you use Terraform, it's very, very important to always explicitly denote the dependencies between different parts of your desired state, so that Puppet knows in which order it needs to execute in order it needs to take these actions. Puppet is an agent system. An agent connects to a master to fetch the desired state, and you modify servers by defining resources. Puppet is also cross-platform, but in the same sense, most often than not, your desired state models will not be cross-platform, but you can use the same tool on multiple platforms. Puppet is also focused on managing operating systems and managing applications. It's not really focused on managing cloud resources. You can do it, but I wouldn't recommend it. Puppet ecosystem, as all the other tools, Puppet has a lot of additional resources at, they call it the Puppet Labs Forge. And there's also an enterprise offering, which offers you scalability, a UI, and a lot of enterprise features, such as role-based access control. Then another product I want to talk about is Juju. Juju is a configuration management tool deployed, created by Canonical. It's also a 100% declarative configuration tool, and it is a tool made by agents. Desired state models in Juju are simply called models. Finally, a tool with easy naming convention, and you modify servers by deploying charms, and then the model describes which charms you want to deploy. I add Juju here because even though it's kind of a niche offering, Juju is a very good tool for very complex and interdependent applications. So, for example, let's say you want to deploy OpenStack. If you've ever deployed OpenStack, you know that OpenStack consists of hundreds of different services that need to be interconnected, need to connect to each other, need to be configured. And any one of these services, you can just swap it out and put an alternative service in there. Judo is great for applications like that. Same with Kubernetes, for example. Judo is a great tool to have an enterprise, to deploy an enterprise Kubernetes platform, because you can just mix and match and get your own customized Kubernetes, and Judo allows you to do that. Judo is great at managing cloud resources, managing operating systems, and managing applications themselves, but it has no offering for CI/CD. One of the reasons why Judo is so great for these complex applications is because Judo uses the concept of relationships. This is quite novel. Most other configuration management tools don't really have this concept. Judo relations basically allow an application to reconfigure itself based on what components are connected to it. A simple example, I think it's on the next slide. Yeah, so a simple example is, let's say you've used Judo to deploy a Wikipedia alternative, MediaWiki. Let's say you've used Judo to deploy this Wikipedia alternative, but now you get a lot of traffic and you actually want to put a caching reverse proxy in front of it. Doing that with Judo is incredibly easy. You just deploy HA proxy, which is a reverse proxy, and you explain in your model, you explain that you want to add a relationship between HA proxy and this Wikipedia instance. And then HA proxy and this Wikipedia instance will reconfigure itself. They will both reconfigure themselves in order to use HA proxy as the reverse proxy for this Wikipedia instance. And so for more complex applications like Kubernetes, this is great. So let's say that you have a Kubernetes cluster and it uses Flannel for a container networking. But you want to use another tool for container networking. Well, that's very easy. You just take out Flannel and you put in, for example, Calico, and you connect Calico to your existing Kubernetes cluster, and the entire cluster will reconfigure itself in order to use Calico for networking instead of Flannel. It's the same with the container runtimes, for example. Let's say you're using container D as a container runtime, but you want to add more security and you want to switch to kata containers. Very easy, just you remove the container D charm, you add the kata containers charm, you connect it to the Kubernetes cluster, and then every instance will reconfigure itself in order to use container D. This is why I included Judo in this presentation, because even though it's a very niche offering, it's very, very good at managing these highly complex, highly interdependent applications, thanks to these Judo relations. Judo also has an online repository of resources, which is Charm Hub. These are high-level pieces of automation code, which can be written in any language, although Python is best supported. The final thing I want to add is that when you use Judo as a system administrator, it is very, very common that you will have to start writing charms, because it is so because these charms always reconfigure themselves. This means that if you have a very niche infrastructure or a very niche requirement that is not already part of the existing charm, that the existing charm does not understand, then you will need to get your hands dirty, start writing Python code in order to either change that charm or create a new charm. This is why Juju often has a much higher barrier to entry, because it often requires you to actually start writing Python code in order to get the infrastructure that you want. Juju also allows you to reuse existing automation code. In a charm, you can use Python, or you can simply use Puppet, or you can use Chef or Docker containers or Bash in order to actually manage the applications. Then finally, for people who are interested in Windows, I just wanted to add desired state configuration is a thing. This is Microsoft's offering for infrastructure as code model. I just wanted to add it here that it exists. You can use it to manage the Windows operating system and use it to manage applications on top of Windows, if that's what you need. But I see that we are a little bit after 11. So I propose that we do a short break here. Let's resume this session at 11:20. Then after that, I will give a short explanation about Kubernetes.
Thank you, Merlin, also for the first part of the presentation. I think this is also a good moment. If there are questions in the chat, you can write it and probably we can answer those after the break.
Yes. after you submit the first version to come back. All right, so we can continue with the second part of this webinar, talking about the Kubernetes as an API paradigm.
Yes, maybe Merlin, before we continue, just a couple of questions that I have. One of the two is you showed that there's actually even greater landscape in terms of solutions. And if I'm not mistaken, you didn't show any specific tool that is mainly used for CI/CD. Is there something there? Is there a reason why? Can you explain a bit more in that sense?
Yeah, so because CI/CD is basically its own completely separate topic, I haven't really, I'm not going to go that much deeper in it. Right now, I have to admit that some of the most competitive CI/CD offerings are simply the ones that are baked um, um, into your source code forge. So GitLab, for example, GitLab and GitHub, their CI/CD offering is actually becoming incredibly competitive. In the past, a lot of companies used separate products for CI/CD, like Jenkins, for example. But I would say that at this point in time, I would recommend most companies to simply use either GitLab CI/CD or GitHub CI/CD, because that will be that will do most of the things you actually need to do. And with both of these tools have the concept of a remote worker, which is basically a very configurable way in order to connect your CI/CD system into any other system that you would want to use in order to deploy and build software. And because of that, yeah, that's what I would recommend.
Yeah, perfect. Thank you. And another question that I got actually more than once is if I'm already using specific infrastructure as code tools that are provided by the cloud service provider, for example, like CloudFormation or the Azure Resource Manager, why should I look for an alternative? Do you have any recommendation in that sense?
Yeah, so the big reason why that this can be a challenge is the issue of vendor lock-in. So basically, every single tool that I've talked about here, every single tool is cross-platform and cross-cloud, which means that if you ever want to go into a hybrid cloud scenario, for example, combine an AWS deployment with a local vSphere deployment, or if you want to go to multi-cloud, like use some spot capacity on either AWS or GCE, but run most of your other infrastructure on one of these clouds. If you ever want to do those things, then doing those things while you are using your cloud specific infrastructure as code tool, that's going to be a big challenge, because then you need to completely re-educate your operations people in order to use another tool. And then if you re-educate them, for example, to use both GCE's infrastructure as code tool and AWS's code tool, then you're still locked into those two platforms. At least the tools that I'm explaining here, at least these tools, you don't actually need to relearn these tools themselves. Even though you can't just move your models from one cloud to the next, you can very easily have a single model, a single desired state model that has resources both in a local cloud and in multiple public clouds in a single desired state model using Terraform, for example. And then another advantage is that a lot of these tools go a lot further than the traditional cloud resources. So for example, as part of my work on Ubuntu, I manage a large GitHub organization of more than 150 repositories. Managing all these repositories and setting permissions for all these repositories, I'm actually doing this using Terraform. And the reason why I can do it using Terraform is because Terraform is such a flexible and such a cross-vendor solution that it also has support for the GitHub API. And so these are tools that if you use AWS CloudFormation, and then you also need to manage internal GitHub organizations or GitLab organizations or any other infrastructure, then you will need to learn a lot more separate tools in order to do all those things. While if you just go with one of these open source offerings that I showed you, it's very easy. They support everything. You don't need to learn a new tool. The only thing you need to learn is what specific resources do I need for then my GitHub repositories, or what specific resources do I need for my local vSphere virtual machines once you start to use that.
Yeah, your answer was perfect. Thank you.
All right, then I will continue with the next part about Kubernetes. Kubernetes itself, it is basically a tool that does everything. Everything from CI/CD, configuration management, provisioning tools, provisioning cloud resources. It basically can do everything, although it initially was simply a platform to manage containers. And so if you go and look at the website, the Kubernetes website, the official summary is Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. Containerized applications is in bold all over the Kubernetes website. However, in my opinion, Kubernetes is more than a container orchestrator. Specifically, Kubernetes is becoming a standardized API to interact with your code that manages your applications and your infrastructure. And it's also a standardized API for this code to interact with each other. This is the difference between Kubernetes as a platform, which you see here. Kubernetes as a platform, that's a traditional way of using Kubernetes, where it's both the control plane and the data plane. With data plane, I mean the data plane are the containers that run your applications and the container that runs your databases. You can use Kubernetes to run all these things. And then the control plane are Kubernetes controllers that manage your application, that manage your database, that add CI/CD, that add things like monitoring and eventing and things like that. Everything runs inside of this single platform. That's the idea of Kubernetes as a platform. However, what we're actually seeing is a shift from Kubernetes as a platform to Kubernetes as an API, where only the control plane runs inside of Kubernetes. You simply use Kubernetes as the standardized API to interact with your automation code and for your automation code to interact with other automation code. And then the actual services run somewhere else. This is an example of Amazon, because Amazon has a very interesting blog post about the difference between Kubernetes as a platform versus Kubernetes API. And this shows a Kubernetes deployment where everything, your application actually runs inside of, it's all Amazon infrastructure. Nothing is actually running inside of Kubernetes, but you are using Kubernetes as a sort of configuration management tool to deploy and manage these other cloud resources. And the reason why this is possible is because Kubernetes itself as a platform is both from the user facing and internally is built on the desired state principle. So every single piece of the Kubernetes control plane is what we call a reconciliation loop that observes the desired state and then adjusts the current state in order to align with the desired state. And this happens with controllers. And so most of the controllers, if you've ever used Kubernetes, you have interacted with controllers, often without even realizing it. When you create a pod or a service inside of Kubernetes, inside of the Kubernetes control plane, there's a controller that watches the Kubernetes API and gets a notification every single time a pod specification gets created or gets updated. And then it checks the pod specification, that's the desired state, and then it updates other system resources like containers, like volumes, like IP tables rules. It changes these system resources in order to get the actual state into the desired state. But we can actually extend this API. So Kubernetes by default has, you can deploy pods, you can deploy services, you can deploy network overlays, but you can actually add new resources, custom resources to the Kubernetes API that allow you to specify other, that allow you to, in your desired state model, specify other resources, things like distributed storage solutions, for example, like a Ceph cluster. Here you see on the left, you see an object, desired state model that specifies, hey, I want a Ceph cluster inside of my Kubernetes cluster. And this is of the kind Ceph cluster. Kubernetes by default doesn't understand what a Ceph cluster is, but by installing the rook operator, then the Kubernetes API is extended, and now it knows what a Ceph cluster is. And then if you're in your desired state model, when you specify the Ceph cluster, then it will deploy all these pods and containers and services in order to have an actual Ceph cluster inside of your Kubernetes cluster. And this basically is slowly turning Kubernetes into the default platform for automating operations. There's a lot of existing operators already out there that allow you to reuse codified operational knowledge for example, how to do encrypted virtualized storage or zero trust virtualized storage. You can use the Rook operator for that, which expands the Kubernetes API with additional objects, with additional resources that you can use to deploy this virtualized storage. Same with the Open Policy Agent, the Open Policy Agent operator for deploying security policies inside of your cluster, or Linkerd in order to deploy zero trust communication inside of your infrastructure. And because all these operators, they use the Kubernetes API constantly, this zero trust communication, normally that's not just a piece of software that you can deploy, because it needs to integrate in your entire existing infrastructure. However, because in a Kubernetes cluster, everything is already available inside of this Kubernetes API, the Linkerd operator can simply connect to all your services and then reconfigure your services in order to add zero trust communication to them. That's the real power of Kubernetes. And you can go really far with this. Ingress controllers that connect to physical switches and routers and load balancers inside of your own data centers. Same with overlay networks that actually use your Calico, that actually use your Cisco switches and reconfigure your Cisco switches inside of your data center from Kubernetes. Provisioning virtual machines in VMware vSphere and deploying Kubernetes clusters on top of those virtual machines. This is also something you can do using Kubernetes. Same with, I gave the example of AWS infrastructure. Every single piece of AWS infrastructure you can request using Kubernetes controllers. Same with cloud service integration. For example, adding virtualized storage to Kubernetes is as easy as deploying the Rook operator, creating a desired state for your Ceph cluster, creating a desired state that allows you to then create new volumes that you can connect to your pods inside of Kubernetes. And all these things are all happening inside of the Kubernetes API. Same with, let's say you want self-service Kubernetes clusters. The platform that we make available to you, make available to OpenCloudification members in order to test out Kubernetes and test out cloud-native technologies, what we call Cloud Native Lab. This uses Kubernetes in the backend. It uses Cluster API vSphere in order to provision vSphere infrastructure. It uses Cluster API Kube ADM in order to then deploy Kubernetes clusters on top of those virtual machines. And it uses the vSphere CSI driver in order to then connect the containers in these virtual machines, connect them to vSphere Cloud Native Storage in order to use your virtualized vSphere storage for your containers. This is all happening with Kubernetes as an API, Kubernetes as the control plane to manage other infrastructure. So finally, one of the last things I want to talk a little bit about are infrastructure as code design patterns. So the first, I've talked a little bit about this automation fear cycle. This automation fear cycle sometimes also happens with infrastructure as code tools. Part of this is because a lot of the current generation of infrastructure as code tools are not completely declarative yet. However, a very good solution to this automation fear cycle is simply to continuously execute your code. Continuously execute your infrastructure as code. This means that, let's say that something goes wrong and you SSH into one of the servers in order to make a manual change. The next time your infrastructure code will automatically execute, it will revert those changes. And this at first sounds like something you don't want. But this means that the configuration drift that I talked about at the beginning of this presentation, the configuration drift becomes impossible. When your infrastructure as code tool continuously re-executes in order to bring the server back into the desired state, this ensures that your desired state, your infrastructure as code, and your deployed infrastructure, that they match 100%, and it becomes impossible to make manual changes outside of that. This is a great design pattern for getting the best from your infrastructure as code tools. This basically forces the system administrators to make any changes they need, to make any of those changes in the infrastructure as code itself, instead of going manually into the servers. When you have a team that is slowly moving from manual operations to infrastructure as code, this is a great way in order to actually get out these old habits of manually changing this infrastructure. This is also called unattended automation, basically. Tools that run on a schedule to apply, reapply, and update the configuration. The benefits are that you discover problems with your infrastructure as code quickly. You force yourself to fix those problems in the infrastructure as code instead of in the infrastructure itself. You force yourself to improve the tools and processes, and you discourage out-of-band changes. Another concept is the reuse of definitions. It is very, very important to reuse the exact same infrastructure as code definitions, both in dev, in stage, and in production. This way, you are 100% sure that if your application works in dev, it will also work in production, because you know that the infrastructure in production is the same, because it comes from the same infrastructure code. Another important design pattern is cattle, not pets. With infrastructure as code, we want to get into a system where we see all of our servers as cattle instead of pets. So what we mean by this is that pets are indispensable and unique systems that can never be down. Pets are typically manually built, managed, and what we call hand-fed. During a failure event, pets need to be manually nursed back to health. It might be a little bit of a gruesome example, but let's imagine somebody runs over your cat. They cannot simply replace your cat with another cat that looks the same. Like it's a pet. This doesn't work. But this does work with cattle. If somebody runs over a cow, you don't really care which cow that was. You just want another cow with the same specifications. And so cattle, in terms of services, cattle are arrays of more than 2 servers that are built using automated tools and are designed for failure, where no 1, 2, or even 3 servers are irreplaceable. Typically, during failure events, you don't need human intervention, as the array of cattle exhibits attributes of routing around failures by restarting failed servers or replicating data through strategies like triple replication or erasure coding. And so the whole idea of this in context of infrastructure as code is that you shouldn't care whether a certain server gets removed and then gets recreated using your infrastructure as code. If your infrastructure as code describes everything that you need your infrastructure to be, then you can just delete your entire infrastructure during a certain, during a maintenance window, for example. You can delete your entire infrastructure, recreate it using your infrastructure as code, and you shouldn't actually care. This is a very, very important design pattern in order to get the best benefits from infrastructure as code. Another issue we often see is the issue of duplication. Once an organization starts to mature in its infrastructure as code journey, we see that multiple teams often use similar systems. For example, let's say your team creates a microservice architecture, which often means that multiple teams will need the copies of the exact same database. Then the question is, how do you actually share infrastructure code between these different teams? Because they often need the exact same database clusters, but they are owners of their own infrastructure as code. So the first way you can solve this is simply by forking definitions. When one team already has infrastructure code in order to deploy a database, then you can another team can copy this code, change some of the values in order to adapt it to their use case, and then keep using that code. This has big advantages. It has the advantages that you avoid tight coupling, you can handle diverse requirements within teams. Teams don't have to coordinate when they change some of the infrastructure code, because after you've copied the code, there's no link back. However, this has the disadvantage that you can have a lot of diverging and inconsistent code. And this can become an issue, for example, for security reasons. Let's say at a certain point, new regulation comes out that requires certain encryption of your database. Now you need to go to the infrastructure code of every single team in order to modify it so that the database is encrypted. So one of the ways in order to handle this divergence and inconsistency is by reusing code with definition libraries. Definition library is basically you have a separate team, often a platform team or an infrastructure team, that is building a whole bunch of templated infrastructure as code libraries. For example, to deploy a database using the company best practices and then using the encryption that is required by this new legislation. And all the teams, they simply import this definition library into their infrastructure as code solution. They modify certain, they input certain variables, for example, in order to modify it to their specific use case. And then they use that combination of code in order to deploy their infrastructure. This has the advantage that if you want to make company-wide changes, it's very easy. You only need to change it in one place. However, this has a couple of challenges, specifically around tight coupling. One of the most important parts of DevOps is to unblock teams, to give teams the power and freedom to set up their own infrastructure, to make changes without having to coordinate with 10 different other teams. So it's very, very important to remember that these definition libraries, they should still avoid tight coupling so that teams can still change some parts of the standardized definitions without actually having to coordinate with multiple other teams. So the guidance, one of the guidance is to use separate pipelines for each. And use CI/CD and order dependency testing strategies. Let's look a little bit more into what I mean by that. I call this a library pipeline. This is basically tests shared. This is basically the idea of testing shared definitions before pulling them into dependent pipelines. Let me give you a practical example of what we're trying to solve here. A certain team is constantly updating their service, which means that their own CI/CD pipeline will build infrastructure using their infrastructure as code, then test that infrastructure in their pipeline, and then once all the tests succeed, it gets deployed into staging or deployed straight into production. But now let's imagine that the team makes this team makes a certain change. They start a new infrastructure pipeline, and just by chance, this library definition also has a change at that point. If they don't have separate pipelines for this, if the build pipeline of the team always pulls in the latest version of the library, then when a test fails, there are multiple reasons why a test might fail. It might be because of the team's own changes, or it might be because of changes in the library that they might not even know that happened. And so this can create a lot of frustration between teams. When another team is constantly breaking your build pipeline and you constantly have to debug your build pipeline because another team broke it, that creates a lot of frustration. And that is why if you use these templated libraries, it's very important to first have a pipeline that tests the new infrastructure code with the old service code. If the new infrastructure code works with the old service code, then you know that there is not an issue in your new infrastructure code. And only when those tests succeed, only at that point are the new versions of these libraries, are they included in the new versions of in the new service build pipelines. You might recognize that this is something that is not unique to infrastructure code. This is something that is actually very, very common for regular code too. If you have shared libraries inside of your company, shared development libraries, JavaScript libraries, you have the exact same issue and you can solve it using the exact same methodology. And that's why in the beginning of this presentation, I said the whole point of infrastructure as code is to use all this existing knowledge that we have about software engineering to also apply it to IT operations, to also apply it to infrastructure, because this shows that you can then very easily solve infrastructure problems using the same methodology that you use to solve software problems. Another issue are shared elements. For example, your company has a microservice architecture behind a load balancer. There's a whole bunch of microservices managed by different teams, but then the load balancer itself, it has certain shared components and it has certain individual components for each service. So how do you actually deal with this? Well, the way that you deal with this is to avoid monoliths. It's again the same concept of microservice architecture for software engineering, for development. We can now also have microservice architecture in our infrastructure code. So the first step is to try to avoid instances that actually share infrastructure code between different teams. But you can't always remove any dependencies between these infrastructure code. So if you have dependencies between this infrastructure code, then you need to optimize the shared infrastructure code in order to simplify making changes. This, for example, means that your shared code, for example, might be a shared definition that then pulls in a whole bunch of libraries. And each separate team creates their own library, can change their own library that are then pulled into the shared code. As a final part of this presentation, I just want to talk a little bit about declarative Linux, because this is a very interesting development that is happening right now inside of the Linux ecosystem. As I said in the beginning of this presentation, Linux itself is inherently imperative. Linux itself is not declarative. For example, if you want to change the network configuration of a Linux machine, the way that you do that is by calling certain APIs of the Linux kernel and saying, okay, now add this IP address, this interface. Now turn on the interface. Now create a route. Now do this, now do that, now do that, now do that. There is no way to simply describe your entire network configuration that you want and then give it to the Linux kernel. That just doesn't exist. Which means that, for example, during boot up a Linux server, some Linux servers are insecure during boot up because, for example, it might already configure certain network interfaces, but not have configured the firewall already. Because of this, it's often very important to take good care of, okay, what is the order in which I am configuring this Linux machine? However, because this is very, very complicated in order to make it secure, and because this requires very in-depth knowledge about how Linux actually works, there are a lot of tools to help you with this, specifically NetPlan and systemd networkd. NetPlan and systemd networkd are declarative configuration daemons for Linux networking. They basically work by a system administrator writes in a YAML or in a JSON file what configuration they want for the Linux system, what network configuration they want. And during boot up, these daemons will take care of configuring all the low-level Linux network interfaces in the exact correct order to make everything secure, to make everything stable. Moreover, these daemons will actually keep watching the network configuration. They will subscribe to a lot of events of the Linux kernel. And when anything changes in the network configuration, these daemons will change it back to the desired state. The main difference between NetPlan and systemd networkd is that NetPlan is, I would maybe call it a cross-platform tool. So systemd networkd is used mostly on servers, while on laptops, most Linux laptops use tools like Network Manager. NetPlan is a declarative configuration tool on top of that can then create manifests for systemd networkd on servers and for Network Manager on laptops. So on servers, you can simply directly use systemd networkd, or if you want to apply certain configurations both to servers and to desktops, you can use NetPlan in order to have a more generic way to configure that. Another example is NixOS. If you're part of the Linux ecosystem, you might start to see more and more people talking about NixOS. The whole idea of NixOS is to create a Linux distribution where every single part of the Linux distribution is declarative, both in how software and packages are compiled and built, and in how the system is configured. And so you basically configure a NixOS system by changing a declarative model of what you want exactly. It is simply impossible to do manual changes on NixOS because the only way how you can change anything is to do this declaratively. Many of the innovations that come out of this project are also included in more traditional Linux distributions. So you definitely don't need to actually switch to NixOS in order to start experiencing some of the benefits of this push for more declarative configuration management in the core of Linux distributions. So as a final announcement, I want to talk a little bit about the upcoming OpenCloudification events. We do a lot more than simply these webinars. On May the 2nd, there is a hybrid, both in real life and online user meeting at the Beacon in Antwerp. anyone is welcome to join us, both online or in person. And in the morning session, we will have a couple of webinars on, for example, how to do IoT data processing with the open source Obelisk platform. This is very interesting for companies that are looking into using Azure IoT Stack, for example. This is a great product that either can serve as an alternative or can serve as a complement to the Azure IoT Stack. We will also have sessions about the Cyber Resiliency Act and cloud native FinOps, how to improve the or how to reduce the costs of using the cloud for your company. Maybe also talk about cloud certification schemes, and we'll also have a short workshop type introduction to how to create or how to set up the best development environment in order to test and develop cloud native applications. Then we will have a lunch where there's networking opportunities and project updates. And in the afternoon, a couple of the OpenCloudification user group partners will do a deep dive into their own cloud environments, where you can learn from some of the companies doing creating cutting-edge cloud infrastructure, and where these companies can get feedback on their current cloud architecture. In June, we will also do a workshop, an introduction to Kubernetes workshop and cloud native applications. This is a workshop that will basically start from zero, from how to use containers up to how to be an expert in using Kubernetes. In August, we will do a webinar about trusting edge devices with remote attestation. Basically, how to solve the issue of you have devices that are not inside of your own data center. You have devices that are maybe in locations that are easily physically compromised. How can you detect those compromises? And how can you ensure that you don't send sensitive data or sensitive workloads to these edge devices? Additionally, how can you have these edge devices themselves detect when they are compromised and then shut down or notify external parties about those compromises? Then in September, we will have a new workshop on Fletch. Fletch is an optimized Kubernetes orchestrator for edge computing, which uses about 10% of the total resources that a regular Kubernetes distribution uses. And where we will also show an integration between this Fletch orchestrator and a remote attestation system, so that you are 100% sure that any device that joins your Kubernetes cluster is a device that is actually running trusted software. Then finally, in October, we will have a webinar about privacy-friendly data processing with multi-party computation. And as a short teaser for this webinar, one of the interesting parts of this webinar is that the traditional view of multi-party computation is that it is something you can use if multiple different parties have data that they don't want to share with each other, but they do want to share computation results of this data. However, what we are working on is actually a system where you can use multi-party computation simply as a single party with data that you want to process on third-party infrastructure, for example, in the cloud, but you want to ensure that the cloud provider does not actually have access to that data. You can also use multi-party computation in order to ensure that the place where your data is being processed still doesn't have access to that data. This is coming in the fall of this year. All right, this is it. If you want more information about infrastructure as code, there's the Infrastructure as Code book of Google. Can definitely recommend that, and Implementing Infrastructure as Code by Keith Morris, which is also a very good resource. If you want to know more about OpenCloudification, you can go to our website, and you can also contact me, send me an email to get more information either about OpenCloudification or about these topics specifically.
Thank you very much, Milan. Top. Great overview again, great presentation. Bit more complex than the previous time, but we got there. And of course, based upon this, we'll be publishing it, and so people can always fast forward you as I do sometimes too. But that's not really necessary because the presentation was excellent, so it's very well as it goes. Thank you very much, Milan, also for noticing and noting the different upcoming events and activities, and we hope that attendees will be able to join there as well. I think for both of us, we wish you a good afternoon or morning, whenever you are looking at this, and hope to see you shortly again in a couple of weeks.
Bye.